Yeah, okay. So back to example 3, what we did before lunch was called, what I call pattern recognition. Just being able to recognize the chain rule expanded, fixing it up. But there's a formal process called U substitution. And here's what it involves. It involves taking the inside function. So your analysis would have to still be the same. 2 factors, the bigger one contains the inside function. I think it's x squared plus 1. And what you do is then you just let u, the single letter, stand in place of the x squared plus 1. So it's like a professional line stander, right? You don't want to stand in line. The line's really long. You just pay someone to stand in your place. And when you get to the front of the line, you say, okay, I'll take over again. You step back in. That's all u is doing, except he's not getting paid. And now what you're going to do is you're going to essentially take your integral that was originally in terms of x and dx, and you're going to write it equivalently in terms of now u and du. So let's go ahead and start trading it out. Let me go ahead and get rid of some of this so we can see it again. The first thing I'm going to do is, since I called x squared plus 1 u, now instead of x squared plus 1 to the 12th, it's going to be u to the 12th, right? Now what I have left to replace is the 2x dx. I need to replace that with something equivalent in terms of u. And because I'm going to need a dx, we're going to need the derivative. So if you come over here to what you called u, take the derivative of both sides with respect to x. So you get the derivative of u with respect to x is 2x. If you then multiply both sides by dx, you get 2x times dx. And if you remember back in 3.7, we took the derivative this way. We called it differential form. And so you can go straight to that in the future. du on the left, and then 2x times dx on the right. Now look at this. My good fortune. I'm trying to replace the 2x factor and the dx factor. It would appear that I could replace both of them with a single replacement of du, right? So let's do that. The 2x dx becomes du. And what I've done now is I have successfully rewritten the integral to something that's equivalent. And notice now it's much simpler looking. There's no longer 2 factors. There's only a single factor, and it's a single variable raised to a power. So at this point, it doesn't matter if it's u du, p dp, x dx. We could treat it like we would normally treat it with the x to the 12th dx. So this is pretty darn easy. There's nothing to worry about now. It's just the simple power rule, right? What is the antiderivative of u to the 12th? 1 u to the 13th, right? Plus c. Now here's the only deal. The function started off as a function of x. It is currently a function of u. So this would be the time where the line stander, the professional line stander u, gets near the front of the line, and now you need to step back in and assume your rightful position. So we need to replace u with what u is. So we get 1 over 13 times u to the 13th plus c, but I put a parentheses. And now one of my favorite questions. What is u? U is x squared plus 1. Oh, thanks. That's a nice compliment. No one's ever called me x squared plus 1 before. And if you notice, you compare that to what we got by pattern recognition, it's the exact same, right? So U substitution is a formal process, an algorithm that works every time the pattern recognition does. So for us, when we identify the inside function, we mentally check to see if that other factor was the derivative of the inside function, and if it was, we packaged it back up to get rid of it. The U substitution takes the derivative and gets rid of it by replacing it with a single du. So, what's that? It's just another available letter. You can use M, call it M substitution. Yeah. U is easy to write, and it's fun to say what is U. So maybe that's why, right? You kind of feel like you're breaking some grammatical rules and getting away with it. I don't know. But it's another available letter. If you don't like U, Phipps, you may choose another letter. I would say stay away from F and stay away from X. Okay. Yeah, so it is an arbitrary variable. All right, so questions so far? You can tell it's going to be a fun section, right? It'll require a little bit of practice. The easiest way to recognize patterns is to what? Practice. See a lot of things. See a lot of patterns, yeah. All right, so now example 4 says to evaluate this integral. So you walk up to the problem, you like the subproblem, and you identify that it has 2 variable factor groups, right? 3x cubed and the sine of the 2x to the fourth plus 1. There's no product rule for integration, so it's probably going to be U sub or pattern recognition. Which factor has more information? The sine one. Yeah, so if you walk up to the outside of the problem, the first thing you notice is sine of blob. That's going to be the outside function. And ultimately, that's going to involve the antiderivative. What's the antiderivative of sine? Negative cosine. So that's going to be coming up. But first, we have to check. What is inside the sine function? 2x to the fourth plus 1. That other factor of 3x cubed, fingers crossed, maybe when someone took the derivative and they did the chain rule, that 3x cubed came from the derivative of 2x to the fourth plus 1. We'll check mentally. What's the derivative of 2x to the fourth plus 1? 8x cubed. And you compare it to the 3x cubed, and you're like, man, we're so close. We're so close. All we would have to do is take that 3 and kind of complete the left side of it, and now we have it. It's all it takes. But we can't do it that way. So here's the deal. What's important is that you generate the variable part. You get the x cubed part. If you are off by a constant multiple, that is not going to be a problem. You can accommodate constant multiples. You can't accommodate variables being off. So, in fact, here's what I would suggest you do now from the very beginning. Step 1. If you have a constant multiple in the integrand, just pull them out front of the entire problem. Don't even let him have a say in what goes on in the antiderivative process. I call him the writer. He's just riding through the problem. He's a mathematical stowaway, okay? He has no idea. He's there in the beginning. In fact, look, he's already there in my answer. He has no clue what's going on. He's just there for the ride. This is nice, he says. Okay? So there you go. So now we go to the process. Sine is the bigger factor. 2x to the 4 plus 1 could be the inside function. Its derivative is 8x cubed. We get the critical x cubed part. So here's the deal. If our derivative generates an unwanted factor of 8, what would I need to have in my answer to neutralize the unwanted factor of 8? A 1/8, right? If you know you're going to be eating a plate of steamy enchiladas, you could neutralize the acid by taking some Tums or something like that, right? Calcium carbonate. Same thing. You put the reciprocal of your unwanted constant multiple in your answer, and now you've taken care of it. All right? So I call the 3 again the rider. He's just going along for the ride. The 1/8, appropriately enough, I call it the correction. You can make corrections of constant multiples. If it's a number, it's being multiplied through by the integrand, you can correct it. You can't correct variables. All right, so now we're done with the inside piece. This x cubed is essentially gone. You can essentially package it back up inside the inside function. And since that's the only other factor, now you move on to step 2. Step 2 is actually the integration process. Okay? So it's important to know that the first step of integration here is actually taking a derivative. Now, what is the antiderivative of sine of blob? Negative cosine of the blob. And then, of course, you garnish it off with a plus c. So this negative here, originally, when we first did this, was another correction. But now you could say it essentially becomes part of the rule. Now, those 3 types of coefficients, riders, scalar multiple corrections, and rule coefficients, those are the only 3 types of constant multiples you'll ever have in front of a problem. And now, to rewrite the problem, you can combine all 3 of them at once, and you get negative 3/8 cosine of 2x to the 4th plus 1 plus c. And you pretty it up. And, of course, how do you know or check to see that that's right? Take the derivative. Yeah. Like this rule coefficient of -1, sometimes people miss that. The derivative of sine is cosine, but the antiderivative of sine is negative cosine. Because when you take the derivative of cosine, you generate a negative, and you don't want it to be there. So that's why that negative's there. You could also do this with my u sub, and you would let 2x to the 4th plus 1 equal u. Let's try it. Here's what the u sub would look like. you're going to let u equal 2x to the fourth plus 1. So you still have to do the same analysis. I would still recommend bringing the 3 out front. And let me get rid of all this business over here. So you would still want to do all of this part right there. All right, so now let's go ahead and get our integral up and running. It's going to be the integral of, well, it's going to be not sine of 2x to the fourth plus 1, but rather sine of u. And now, since the 3 is out front, I'm going to leave the 3 out front there. He goes along for the ride, whether you're doing u substitution or not. So all I have left to replace here is the x cubed times the dx. So let's take the derivative in differential form. du equals 8x cubed times dx, right? 8x cubed times dx. Well, I'm trying to replace x cubed times dx, which I can see visible right there. So if I solve for x cubed dx by multiplying both sides by an 8, I get 1/8 du equals x cubed dx. And now I can make the replacement. But I can't replace it with a straight up du. I got to put a 1/8 du. Now, because multiplication is commutative and associative, I can put those two factors anywhere I want. The 1/8, I'm going to bring it out front with the 3, and the du will assume his rightful position at the back as the right bookend of the integral. And now if you simplify, you end up with 3/8 sine of u du. And again, what u substitution does is it takes away the product nature and turns it into a single function integrand. What's the antiderivative of sine of u? Negative cosine. So you get negative 3/8 cosine of u plus c. And then the last thing you do in u sub is you replace u with what u is. And in this case, u was 2x to the fourth plus 1 and then plus c. And that's the same answer we get. So if you feel like you need to do u substitution each time because you like it better, it feels better, it's a systematic process, that's fine. Do that and try to get better and better with the pattern recognition. You'll be doing yourself a favor. Okay? All right, example 5. I'm going to give you, I'll give you a minute or two, a minute and a half, to chew on this one by yourself and see how far you can get. Rewriting it is still going to be the key. Constant multiples up front. You're going to want to get rid of radicals as if you were taking the derivative and write them as rational exponents. But try to do it by pattern recognition, because that's kind of what I'm going to be doing. I'm not going to be doing u substitution anymore until it's absolutely necessary, and I'll tell you when it's necessary as we get deeper into the lesson. Don't forget your dx at the end. That's 2 minutes. You don't have a lot of examples to pull from, but the more you work, the more systematic it'll get. And it does become a systematic process. You notice you have x plus 1. That's a variable factor. The cube root of x squared plus 2x is another variable factor. And you're dividing by pi. So when we say factors, it's the same as if you're multiplying or dividing. It doesn't matter. Is pi a variable, though? No. It's a constant, and it's a factor. So that's what you want to pull out front. So dividing by pi is the same as multiplying by 1 over pi. So that's the first thing I would do. Pull the 1 over pi out front. You got x plus 1 here. And then the second factor is x squared plus 2x to the 1/3 power dx. Now with two factors, you're going to look for the bigger of the two, which looks like the second factor, right? So you got to identify the inside and the outside. If you walk up to the problem, the first thing you run into is blob to the 1/3. That's going to be the outside function. And everything on the inside could be the inside function. You just have to check. Is that the thing you would call u? Is that the inside function? Well, let's see. The criteria is, does the derivative of that generate all the other factors, or only off by a constant multiple? What's the derivative of x squared plus 2x? 2x plus 2. Lay bummer. That's French for the bummer. It's not 1x plus 1. It's 2x plus 2. So are we out of luck? No. Good. If you factor out a 2, you're left with 2 times the quantity x plus 1. And now you're like, it's going to work. We're going to get it. I get the critical x plus 1 part. I'm only generating an unwanted factor of 2, which is not a problem. So at this point, you get excited because you know it's going to work. You know it's going to work. So you go to your answer line, 1 over pi. There he is. What's going on? Don't worry about it, 1 over pi. If I'm off by a 2, I have to have a what in my answer? A 1/2. There will be answer choices on multiple choice where there's a 2 there instead of a 1/2. So remember, if you generate an unwanted number, you got to have its reciprocal there. And now the x plus 1's work is done. It gets packaged back up. You can kind of forget about it. And now you move on to the second part, the rule of integration, which involves the outer function, blob to the 1/3. That's like x to the 1/3. It's going to be a power rule. Blob to the 1/3 becomes blob to the 4/3, right? And then instead of dividing by 4/3, we multiplied by 3/4. The only difference is it's not just x to the 1/3. It was blob to the 1/3. So now it's going to be blob to the 4/3. And before you get excited and walk away, remember, you're always celebrating with the plus c. Think about it that way, celebrating with the plus c. So we have our rider, we have our correction, and we have our rule coefficient. Those are the three, those are the most you'll ever have, those three, or any combination of them. And now you can clean up your final answer, multiplying all your coefficients together. You get 3 over 8 pi, and you could call this the cube root of the quantity x squared plus 2x to the 4th power and plus c. So systematic procedure helps you recognize patterns. Add grouping symbols, get rid of radicals, coefficients out front. It doesn't matter how many factors there are. If there's more than 2, then only one of them is going to have the inside function whose derivative generates all the other factors. And of course, you could check. Take the derivative to check, and I would recommend that as you do your worksheet in the beginning. It reinforces what you're doing. Because invariably people always ask, where did the x plus 1 go? And of course, the answer to that is what? What? It went back in the box, right? It got packaged back up in the box. We're undoing the chain rule. Chain rule unpacks boxes, anti-differentiation, chain rule reverse packs them back up. Okay, so example 6, we're not going to get all the way through it by the end of the day, but it's kind of nice because, as it says, every single one of these has the same inside function, but a different outside function, and therefore a different rule of integration. There can only be one rule of integration. It says to evaluate each. Okay, so here we go. 5 sine of 2x times e to the cosine of 2x power. I spy a 5, so I'm going to bring it out front. And you don't physically need to bring it out front if you just can ignore it in your analysis. So he's already in your final answer. There he is, waiting. See? Waiting. Now, of the two factors, which one has more information? Because you do have two factors. e to the blob, right, because the sine of 2x has 2 layers, and e to the cosine of 2x has 3 layers. So the second factor is going to be the one you focus on. And if you walk up to it, the first layer you see is e to the blob. That is, again, your outside function, and will ultimately, not yet, involve the rule of integration. So now you look inside there, and you're like, hey, I spy a cosine of 2x. That's going to be what you would call u, or your inside function. Notice it itself has 2 layers, right? But there can only be 1 layer to the outside. So now cosine of 2x will check. Could it be that sine of 2x, the other factor, came from the derivative of cosine of 2x when the chain rule was applied? Let's see. What is the derivative of cosine of 2x? -2, right? -2 sine of 2x, yeah. Because the derivative of cosine of blob is negative sine of blob times the chain rule itself, another 2. And if you compare it to sine of 2x, remember the 5 doesn't even weigh into it. We get it, right? We get the critical sine of 2x piece. We are only off by a -2. So the 5 has been waiting, probably impatiently, and now we have to have a correction of a what? A -1/2. And at that point, when you put your correction down in your answer, all the other factors but the outside function, they've served their purpose. They're gone. Package them back up inside the exponent and forget about it. And then you take a quick break, breaks over, and move on to the second part, which is the actual integration process. What is the inside function actually inside of? It's inside of e to the blob. And what is the antiderivative of e to the blob? The antiderivative of e to the blob is e to the blob, right? If you're your own grandpa, you are also your own grandson. And you get excited and you stop and you walk away there. And you lose points, right? Plus c. Clean it up, you get -5/2 e to the cosine of 2x plus c. And of course, if you take the derivative, you can check to see that you got it right. Now, one more word about this. If you are in the habit of looking for the inside function before identifying the outside function, which would work if you're kind of struggling, you might say the inside function, which has to be in the second factor, is 2x, right? After all, 2x is in fact inside of something, right? But let's check. The derivative then of what you're calling the inside function would have to generate the entire other factor. What is the derivative of 2x? 2. Does that generate the sine of 2x piece? No, we are off by variables. We don't even generate the variables. So what that means is you took too small of a bite. That's not the correct inside function. So work out another layer, grab the cosine now at the 2x, and you'll get it. Okay, so if you want to work that way, that's fine. It's easier, I think, if you identify the outside function and then look immediately within. Your inside function may have 2 layers, 3 layers, 4 layers, okay, because it has to generate all of the other factors but the main one, okay, the biggest one. All right, the next one, 7 sine of 2x, cube root of cosine squared of 2x. Yowza. Take 1 minute and do it yourself. plus c. If you're taking a test and you don't know what the answer is, don't just put plus c. Put a function in front of it like x plus c or sine of x plus c, and then you could possibly earn credit for at least having the plus c. All right, going through the motions here again, I spy a 7 coefficient, so I'll pull it up front. You got sine of 2x. I then have another factor that can be written as cosine of 2x quantity to the what power? Well, it's to the 1/3, but it's also squared, so I would call it to the 2/3. Yeah. And so now your outside function could be blob to the 2/3. And that's going to ultimately involve the antiderivative using the power rule. But before we get there, we look inside and we spy cosine of 2x. That could be the inside function. I always want to say could because you can't assume it. You have to check it. What's the derivative of cosine of 2x? Does it generate the sine of 2x? Well, we know it's negative 2 sine of 2x. So yes, again, we pick up the important variable part. We're only off by a negative 2. So at this point, it's going to work. 7 goes along for the ride. We'll have a correction of negative 1/2, the reciprocal of the unwanted negative 2. The sine of 2x gets packaged back up. And now the rule of integration. Step 2, blob to the 2/3. When you add 1, becomes blob to the 5/3 with a 3/5 in front. That's your rule coefficient plus c. And of course, the blob is just cosine of 2x. And there's your answer. And now it's just a matter of tidying it up a bit. You get negative 21/10 cube root of cosine. You can write it back in condensed form. Cosine to the 5th of 2x plus c. And look how wonderfully fun and easy it is. Wonderfully fun and easy. We got like 2 minutes left. I want to jump back up here to example 2. Just one little note here. No, it was example 3. Remember that 2x? He was so perfect. The derivative of x squared plus 1 generated the 2x. And so we included it as part of the inside function. Here's what you could do. In the future, you could just say, you know what? I don't care. I'm going to pull the 2 out front. And I get x times x squared plus 1 to the 12th power. So now notice the 2 is already in your final answer. Now you could say the derivative of x squared plus 1 was 2x. And I generated an unwanted 2, right? So I'll have a 1/2 correction. And now the x gets packaged up. And it becomes 1/13 x squared plus 1 to the 13th plus c. And what's going to happen with the 2 and the 1/2? They'll divide out anyway. So you don't even have to consider if the existing coefficient is going to be part of the perfect derivative, because it rarely is. But even if it is and you want to bring it out front, it'll always work out that way. It'll work out beautifully. All right, so we'll stop right there with example 6b. This is one you're going to probably want to hit the worksheet early, start practicing. Don't forget to turn your calculators in. You can go. Have a great day.